I'm going to talk about, so switching gears to machine learning. And so I'm going to talk about two different things, somewhat related. So large-scale learning with kernels, and I'll introduce an open source software project called Skylark. And, but let me start on a little bit more of a casual note, which is that I was on this long flight, 6-hour flight from New York to Berkeley the other day. And I wasted some of that time thinking about if I wanted to show one picture to my audience about big data challenges, what should it be? So after some thought, I came up with this. I guess this deserves some explanation. But this is one of those ink blot, personality tests that psychologists would give you, and then they would say, okay, what do you see in this picture? And then based on your responses, and there's a diversity of responses depending on your background, they try to sort of do some psychoanalysis. So why is this related to big data? You can have an ink blot type of test for big data, which is the following. So I give you a problem. So I give you XY pairs, and I say train lasso on this problem. I have n data points. The data lives in RD. N is 1 billion. D is, let's say, some high dimensional thing, so 10,000. And then I ask you, what do you see, right? And there are a variety of responses. If you take a pure systems point of view, you do a back of the envelope calculation and you compute the size of the data, and it's 80 terabytes. And so you think of MapReduce scripts running on a Hadoop cluster, let's say. If you do numerical linear algebra, particularly the flavor that Ilse and Michael have been pursuing, then you start thinking of framing lasso as this, maybe like a constrained least squares problem with, so I have a least squares objective function with an L1 norm constraint, and maybe you want to do sketching because this matrix has a column space that is a compact structure in this high dimensional space Rn, and maybe by using sketching you can reduce dimensionality and you can scale things up. But the metrics here, the point I'm trying to make is, the systems folks have a metric, which is how quickly I can run this on a cluster. If you take a pure numerical linear algebra point of view, your metric is somehow guaranteeing the quality of the residual at the end of the numerical linear algebra computation. And if a statistician comes in, their point of view is that the data is actually sampled from some distribution, and you've made assumptions. You've made an assumption that XY pairs are related through a linear relationship, and that relationship is highly sparse. And so you have things like, they would state a theorem like this, which would say that with high probability, when you sample from this distribution and acquire a training set, you don't need that many examples. I mean, something like 1 over epsilon square log. So let me not read all that, but the theorem would basically say that if you care about generalization error, you probably don't need.
Is it possible you have your cell phone in your pocket?
Yes.
I'm getting some feedback on the
Okay. What should I do?
mic. Just set it aside.
All right. So the statistician's point of view is that having made this assumption about linearity and sparsity, you don't need that many examples to estimate the best linear model under this sparsity constraint. And so what is the point of this exercise? I mean, I guess some things are, while being obvious, are still worthwhile to state, which is that big data machine learning, if you think of building a stack, requires conversations, which is why meetings like this are so valuable, because the metrics across the stack are completely different. And the other point, which is getting more to the kind of the technical meat of this talk, is that as the data sizes increase, you want to avoid strong assumptions, making strong assumptions like linearity, sparsity on the structure of the model upfront. And so you want to go towards non-parametric models. By non-parametric, we'll again give a casual definitions, models that grow with the data, and you're not imposing some functional dependency, functional form on this dependency upfront, right? So you want to look at non-parametric, nonlinear models, and to some extent, this is what might be going on behind the recent success stories around deep learning, right? Which is to match big data with big models. And so there are these spectacular gains on image classification or the Facebook deep-face system, which is really having access to a large labeled data set and then marrying it with the right sorts of highly nonlinear models to gain like big gains in terms of metrics that these communities care about. And the other point is that if you have a linear modeling problem or a linear least squares type of problem, the complexity of solving that exactly is something like order ND square. And so if you might take the stance that I'm going to just throw computational resources at the problem, and for practical reasons that might be enough. But this is a setting where distributed computation alone will not get you there because the training complexity is cubic in the number of samples. So distributed computation will not be enough. You have to have some algorithmic mechanism of acceleration. And the one that we'll be concerned about here is randomization. And with respect to randomization, even that will not be enough because what you have done is taken a humongously large problem, which is a non-parametric, the problem of training a non-parametric model, which is completely impossible, and turned it into a big data problem that still requires distributed computing resources. So you have to sort of do both of these things together. So with that motivation, here's the outline for the talk. So first, I want to give a background for kernel methods, which is a rigorous way to think about non-parametric modeling, the scalability challenges that arise in that setting. And then I'll focus on the random Fourier features technique introduced by Rahimi and Richt, which we'll build on, and which has certain advantages in terms of scalability. Then I'll show some results on applying these techniques to speech recognition problems, where it will turn out that kernel methods can actually match deep learning performance, and deep learning techniques are considered state-of-the-art in this domain. And based on empirical observations there, we'll motivate the need for both parallelization and randomization. And then I'll talk about two different contributions towards this effort. One is to simply take these randomized methods and implement it in a practical fashion with distributed optimization techniques. And the other is to improve the quality of this technique or the efficiency of this technique by essentially a de-randomization approach, which is based on Quasi-Monte Carlo feature maps. And then many of these algorithms are implemented in this open source software library called libSkylark, which was recently released, but it's still work in progress. And this is a much bigger library. It instantiates not only these kernel methods, but also a class of randomized numerical linear algebra techniques, and it's designed for, with the objective of enabling machine learning algorithms at the front end for distributed memory systems. Okay, so this is joint work with several colleagues, both inside IBM and externally. So I'd like to acknowledge Ilse, Michael Mahoney, and Jian Yang at Stanford for this collaboration here. And Ken Clarkson, who's also in the audience, you can approach him to learn more about the Skylark effort. Okay. So now let's just look at some background of kernel methods. The history of the subject, there's at some point it made its entry into machine learning, but the mathematical basis can be traced very far back. And I've chosen to just, cite this reference by Ranjan in 1950, but this has a long history. So you start by taking a symmetric positive definite function k, x comma z, that's defined on an input domain script x, which actually can be pretty much anything. It can just be a set, but for this purpose, we'll assume that it's a subset of Rd. And this symmetric positive definite function, the kernel, gives you access. There's a one-to-one correspondence between kernel and the so-called reproducing kernel Hilbert space, which is a nice space of functions on which learning problems can be posed. So this is a function space with an inner product denoted as follows, and a norm. And you can do regularized disk minimization in this hypothesis space. So you're trying to optimize a mix of a data fit, a loss function plus a regularizer. So the norm gives you control over the complexity of functions, and you're trying to you optimize this over the RKHS associated with the kernel. And so the kernel gives you access to the RKHS, and there is also a backward correspondence, which is that nice function spaces where the norm controls pointwise behavior of the function also has a kernel associated with it. So there is this fundamental reason why these things are important. Now, this is an infinite dimensional optimization problem in general, but because of the so-called reproducing property, it turns out that the representative theorem here says that the optimal function is a linear combination of kernels centered on the data points. So you can take this expansion here and plug it back into this original functional optimization problem and arrive at something that's finite dimensional. And that's the basis of a large suite of algorithms. For instance, if V is the least squares, it leads to kernel ridge regression, or if V is the hinge loss, it leads to support vector machines. Okay, so the issue of scalability. So let's say we are working with the least squares loss, then we are led to solving this large, dense linear system involving the gram matrix of the kernel. And this is challenging because you need order n square storage. You need to solve this dense linear system, so that will be like order n cube complexity. And the killer is really at test time, once you've built the model and you've deployed it for prediction, you need to go back and evaluate the function, which is a linear combination of kernels centered on your data points, and that's a big sum. And so that has order nd complexity. So as the training data increases, your test speed will keep, basically become a bottleneck in deployment settings. And also working with this form explicitly is hard for parallelization, because the kernel, the gram matrix, Ki, the entry I, j, is the evaluation of the kernel on this pair xi, xj. So this pair has to meet somewhere on some processor, right? And so this pairwise nature of the computation makes it hard to parallelize. While if you use the linear kernel, which is just kx, z is x transpose z, then we are back to linear modeling setting, and now you see familiar linear least squares and things like that. So there things are much more scalable. On the other hand, we lose the generality of the full kernel method in the non-parametric modeling framework. So let's talk about randomized algorithms, and there is a large body of work in this area, but we are going to focus on data oblivious feature maps. So these are feature maps psi that will take the input data in RD and map it to S complex numbers. And the complex, the baggage of working with complex numbers is just for notational convenience. But so you have an explicit feature map psi such that the kernel function can be explicitly written as, or approximately written as, the inner product between psi of x and psi of z. So this, basically having access to such an explicit feature map, lets you take your original data matrix, which is x, apply this transformation psi, and arrive at a new matrix, which is z of x. So this matrix z is actually implicitly a function of x. And now this is a linearization mechanism, because you can now, once you have this z matrix, you can go back to just doing linear modeling on this matrix z, data matrix z. So if this, depending on S, the embedding dimensionality, you can improve your storage time. Storage becomes order ns, training time becomes order ns square, and the test speed is independent of n, and that's the advantage of looking at these, trying to create this explicit feature map. So this is data oblivious in the sense that we are approximating the kernel function. We are not even looking at the data to be able to actually do some training here. So we are not going to build a gram matrix and compute its low rank factorization. We are going to get this low rank factorization directly from having access to such a feature map. So the focus here will be on shift invariant kernels, which are basically kernels that only depend on the difference between x and z. This covers a wide variety of kernels, including the Gaussian kernel, which is the most popular kernel in this literature. And the psi is actually a positive definite function. It just means that if I take a finite set of points, evaluate psi, and the matrix that I get is going to be positive definite. So the basis for Rahimi and Recht's random Fourier features technique is this classical result by Bochner in 1932-33, which characterizes the class of positive definite functions. And it basically says that psi is which is a function on RD, complex valued function on RD, is positive definite if and only if it's the Fourier transform of a non-negative measure on RD. So if you like to think of the analogy between positive definite matrices and positive definite functions, then the symmetric positive definite cone is spanned. The extreme rays of that cone are actually the symmetric matrices, rank 1 matrices YY transpose. And here you can think of all positive definite functions as living in this cone spanned by these complex exponentials parameterized by W. So this theorem leads to a one-to-one correspondence between the kernel K and some density P. So if you normalize the kernel, you can have this correspondence between K and for every kernel there is a density P such that you can write the kernel exactly as this integral. So you have this Fourier transform representation. And for the Gaussian kernel, again, the most popular case in the Fourier transform is again Gaussian. So from now on, wherever you see K, keep P in your, at the back of your mind. And so there is this integral representation of the kernel. And what we're going to do is approximate this. So you can think of this as an expectation under P. We'll approximate it by, doesn't really work here. Approximated by a finite sum, so the empirical average. And if you look at that expression in blue here at the bottom, you can actually read off an explicit feature map. So you have psi hat of S, X. So capital S is a sequence of points that you're drawing from the density P, and you're using this representation here, this expansion here, to define an explicit feature map. And that gives you an approximation to the kernel. Okay, so you can now do nonlinear kernel-based modeling on large data sets having access to such a feature map. So now you apply, so this is actually an example from speech recognition, and the data set here is TIMET, which is a 2.2 million, the sample size is 2.2 million, and this is a classic benchmark in speech. So the y-axis is classification error. I think it's a 147 class classification problem. The x-axis is number of random features. This blue line here at the bottom is deep neural network performance. So that's considered state of the art. Now if you want to apply kernel methods and you want to do it exactly, then one strategy for approaching this is to just sample the data and run the exact kernel method. That would give you, this red line here. And now having access to such a randomized technique, you can start pumping in these random features and basically solving a linear problem. And the more random features you pump in, the better your accuracy gets. But there is still some gap here between this green line and the blue line which we want to beat. But at this point, you stop and you say that maybe it's the depth of a neural network that's causing it to have advantages in this modeling problem. But the real reason why people stop is that a MATLAB code like this, starts giving you out of memory errors, right? And this is this shows the simplicity of this approach, which is, you take a Gaussian random matrix, take your original data X, multiply it by the Gaussian random matrix, do this exponentiation, come to this matrix Z, and then you're solving a standard least squares problem there. So now if you push these methods, which means you have to transition from MATLAB and get your hands dirty with distributed computing, then it turns out that the gap between a kernel-based algorithm and a deep neural net basically vanishes. And in fact, in this regime here, this is actually, this classification problem is at the level of frame classification. And if you go to a higher level metric, which is phoneme classification, it turns out that the kernel methods are actually performing better. But this leads to two issues. The first is embedding such an approach or combining such an approach with an appropriate distributed solver, because this matrix Z, this feature transform, random feature transform matrix, at this in this regime of number of random features, like 400,000, this is a matrix. This is a dense matrix, which is around 2.2 million times 400,000. And this is 6 terabytes, right? So you cannot materialize this explicitly and dump it on disk. You have to generate it on the fly, and embed it in a distributed solver, use it, throw it as you iterate. So this requires some effort. The other issue is we don't really want to go so far, hundreds of thousands of features. So how do we actually come up with more effective feature maps? So this leads to 2 lines of investigation. The first line of investigation is simply to try to combine this random features idea with distributed learning with ADMM, the alternating direction method of multipliers, which has become very popular recently. This method is designed to solve optimization problems where you have objective function. The objective function has 2 components, f and g, and the variables involving these components are actually separate. And they're only related via a linear constraint, ax plus bz is equal to c. So what you do is you construct an augmented Lagrangian, and then you do some block coordinate descent on x and z, followed by a dual update. Now there are many variations of ADMM, and the most pertinent for machine learning is this row splitting variant, where your data is distributed by rows. So every row is an example across a collection of nodes. And now, so let's imagine that f is a loss, sum of loss function evaluated on the training data plus and gz is some regularizer. Then what ADMM would do to transform this problem. So now f little I is actually the loss evaluated on the ith block of data sitting on node I, processor I. So the way ADMM would proceed is to split the variables. So introduce xi, which is a local model on node I, and a variable z. So now you have completely split the variables here and added a constraint which is xi is equal to z. So all these local models have to agree with this global model, which is z. And now if you construct the augmented Lagrangian and compute the update, ADMM update equations, it turns out to have this very nice form, which is that each processor has to solve an L2 perturbed version of the, has to minimize fi, its own local loss plus an L2 perturbation. And that perturbation involves access to the global model. So once you compute the local models, you do some averaging, and this averaging is then followed by the proximal operator that is associated with this regularizer, followed by a dual update. So this proximal operator arises in many contexts in optimization. It can be seen as a generalization of the projection operator. So it's just simply, you give it an input x, and the output is y, which is the minimization of this problem of finding the y that's close to x, but which is also perturbed by this, influenced by this f of y. So for any function f, the prox f of x is given by this optimization problem here. So one thing to note here is when you go from an original problem of interest to an ADMM formulation, you're introducing extra consensus variables and dual variables, and you have to be careful on how to manage, and you have to be very careful to manage these things, this extra kind of baggage that comes along. But ADMM is very appealing because of closed form updates. This prox operator actually, for L1 norm turns out to be just soft thresholding, or for the SVM there's some closed form updates, very simple update rules that show up. It's extensible in the sense that the user can just come in and specify their own function and their prox operators, and it generalizes very nicely. It has this advantage, practical advantage of code reuse. So suppose you take our GLM package, which is 800 lines of code, and you want to parallelize it. It requires only 3 lines of change in that code to actually go from a sequential implementation to a parallel implementation. And it has very nice parallelism. So these are some reasons why we want to look at ADMM. So our implementation is going to be, so again, going back to our the problem we are interested in, we call this implicit optimization in the sense that we have this regularized loss minimization, but this data is actually implicitly, it's big data, but it's implicitly a function of small data, relatively small data, xi. We want to solve this optimization problem. Our environment is going to be R nodes with distributed memory. Each node is a T-core machine on which we want to run OpenMP and exploit shared memory parallelism. And so this is this hybrid parallelism setting. So the way we proceed is to chunk up the data y and x by rows, and each block of rows will be owned by an MPI process. And we will do on-the-fly transformations from this the data x to z, and we will think of z implicitly as being block partitioned, and each zij, so zij is a block of z which is living on node I, and j indexes the columns, and j will be allocated to some thread. And now that thread is going to build a local model, and these models are going to coordinate with each other through in an ADMM framework, and therefore solve the problem. And the key is not to materialize the z explicitly, but do it on the fly. Now I'm going to skip through the details of this a little bit, but the main point here is that the threads have to basically compute the prox of f, prox of r, so the prox of the loss function, the prox of the regularizer, and a graph projection step, which is defined as, it's sort of a generalization of the prox, which is given matrices y and x, so matrices y and x are mapped to matrices v and u, which are close to y and x, but which also satisfy this linear equation here that v is equal to zij times u. These are the main steps that a thread will execute, and you can cache some things upfront in the first iteration to make this more efficient. And the main, in some sense, this is borrowing from the formulation of Parikh and Boyd, but to actually make this practical, you want to increase the row partitioning, the column partitioning, because that reduces the cache memory, it reduces the computation, so each computation becomes faster, and it increases shared memory parallelism. But when you increase this column partitioning, some of these variables start to explode. And that can be these consensus and dual variables, and you can avoid this through a careful reorganization of the algorithm, exploiting incremental updates, shared memory access across J, and the structure of the graph projection. We have implemented this in a cloud-like environment as well as on a supercomputer, and it scales quite nicely. And these plots here show the effect of splitting. So the concern here is when you split very finely, either by rows or by columns, it slows down the learning process, but not too much, which is encouraging. And since I don't have too much time, I'll just say it beats libSVM and other alternative solvers out there for the SVM problem. So I want to move to the second part, and I'll probably have only time for a couple of minutes here, but we want to revisit the derivation of the random features method and try to make it more efficient by looking at the underlying integration problem. And what we do here is to invoke QMC techniques, which are designed for more efficient integration. So if you have an integral on the unit cube, you approximate it by a sum here, an average here. The Monte Carlo approach has 1 over square root s convergence rate, and that is slow. So we want to see if we can improve it by selecting a different set of points on which this random feature map is constructed. So the main intuition behind QMC techniques is to actually, instead of doing uniform sampling, do some sort of correlated sampling where things look much more uniform and the quality of integration is improved. And they have this hierarchical structure, which is that the integrand is sampled first at a coarse scale and then at a fine scale as the number of sample points increases. And there's some very rich literature in QMC that characterizes the integration error of a function in terms of a discrepancy measure times how uniform the set S is and how much the function f varies. Let me skip here. There are several implementations available. They are very cheap. These QMC sequences are very cheap to generate, but we treated them mostly as black boxes. And it has been shown that the QMC convergence rate is log s to the d by s, which beats s to the 1 over the Monte Carlo convergence rate. But there is this concern that there is a dimensionality dependence here. But it has been shown in that literature that QMC is actually better for high-dimensional integration, even for high-dimensional integration. So we use this technique. It's actually it turns out to be a minor variation of the random feature approach, but it immediately leads to improvements over the original technique proposed by Rahimi and Recht. So they perform, the QMC methods give better gram matrix approximations, and this leads to some issues about why some QMC sequences are better than others, and whether we can learn sequences that are even more adapted to the problem. And at 6 o'clock, I don't want to go through this. But this is the main theoretical result here, is to motivate a new discrepancy measure that's aware of the class of integrants we have at hand. And this new integration, this new discrepancy measure leads to more effective feature maps. And I'll refer you to the paper. Now, I'll take 1 more minute, because I do want to mention libSkylark. This is the GitHub repository. Basically, so there is a sketching layer in the software which enables a large class of sketching primitives to take a large matrix X and sketch it and produce a sketch S times A. So this is sketching from the left or sketching from the right. And these sketches are then used to accelerate least squares and low rank approximation methods. And then there is this machine learning layer, some of which I discussed here. But the main contribution here is completing this combinatorial zoo of, you have a big data matrix that's sitting either on your laptop or on a distributed, on a cluster, this distributed memory of a cluster, or it could be on disk, and you want to sketch it back to a local matrix because you want to reduce the order ND square complexity of solving the problem on your laptop, or you want to reduce, improve communication, reduce communication by sketching from a distributed cluster onto a single node and then doing operations there. Or you want to avoid disk I/O issues by sketching from taking this matrix on disk and getting it into your distributed cluster, and so you can avoid hitting the disk every time. So the input matrix type, the output matrix type, the local versus sparse matrices, dense versus sparse matrices. For dense matrices, various distributions, 1D, 2D distributions. We are building on elemental and combinatorial BLAS, which are very well written high performance linear algebra libraries. And this is a quick flavor of what the code looks like in Skylark, which is basically what you would write in MATLAB, except that the details of supporting these various combinations and routing, and realizing that the sketching operation is actually, looks like it's a specialized distributed GEM, where one of the matrices is random and therefore does not need to be explicitly instantiated. And therefore, this high performance sketching layer has been implemented, and it's very easy to interact it through a Python front end. Implementation references. I guess I should stop here.